And now you know why that's called a neutralization reaction. Because as we've seen on the pH scale, the acid is at the low end of the pH scale, the base is at the higher end, or the bigger end of the pH scale, and then water as well as the salt are right in the middle in that neutral area. So when we take two things at the opposite end of the pH scale and mix them together, we get two neutral substances. And so that's what a titration does, and again, what we're going to be doing in the lab on Wednesday. We're going to be taking either an acid or a base. We can do it in either direction. In the lab, we're actually going to be taking a base that we know the concentration of and mixing it with an acid that we don't know its concentration. And when we do that and make a salt and water, we can use that information of how much base did it take to react completely with the acid to make a salt and water. That will let us figure out what the concentration of the acid is. So that's what a titration does, is we know the concentration of one substance, but we don't know the concentration of the other. And by mixing them together to make a neutral solution, we can use that information to figure out whichever one of these concentrations it is that we don't know of. No. Okay? So the equation we use, and hopefully this looks a little familiar. Everybody kind of recognize the version of this from last chapter. What are you doing? So if you recognize this, this is our dilution. We've just tweaked it a little bit. So instead of M1V1 is equal to M1V2, we have MAVA is equal to MBVB, which stands for, this is the molarity and volume of the acid, is equal to the molarity and the volume, molarity and volume of the base. And then the only difference is we also have to take into account the mole ratio. So we have to multiply this whole thing by the mole ratio. So it's the same equation as the dilution equation we used last chapter. It's basically doing the same thing. So last chapter we knew the concentration and volume we needed of one thing, and we were trying to figure out the concentration or volume of the other substance to make the diluted substance. This is the same thing. As long as we know three of these variables, we can figure out the fourth variable. So the instruments that we use to do this is what we call a burette. So a burette is this long, skinny glass tube that has measurement markings on it. So this is our burette. And that's what we put this solution that we know the concentration of. So in the lab, this is what the base is going to go in. We know exactly what the concentration is of the base. We'll put that in the burette. And then underneath of it is the solution of the unknown concentration down below. In the case of the lab, that'll be the acid. We don't know we're trying to figure out what the concentration of the acid is, so that's going to go in the flask below. And what we do is we start to add the base to the acid. Oh, I'm getting ahead of myself, sorry. So the standard solution is the name of the solution that we know. So this is going to contain the standard solution. In our case, this is going to be the base, but we could do it in either direction. If we know what the acid's concentration is and we're trying to figure out the base, we just flip-flop these. Okay, so whatever we know the concentration of, that goes in here. That's called our standard solution. And we keep adding this solution to the flask until we hit what is called the equivalence point. And so the equivalence point represents equal moles of the solution. So when we've added equal moles of, so if we have X moles here, and we add X moles here, now we no longer have an acid or a base, we have a salt and water. So once we have equal moles of the standard solution added to our unknown solution, we have done our neutralization, and we now have no longer an acid in the flask, we have a salt and water. And now there's different, as we saw the other day, we can have strong acids or bases, weak acids or bases. So depending on whether we are dealing with strong and strong, or weak and strong, or weak and weak, or whatever, that will vary the pH. But for our purposes in the lab, we're gonna do strong and strong. So a strong acid with a strong base is gonna give us a neutral solution of a pH of 7. So how do we know we've gotten to equal moles? That we've added exactly the same amount of moles of base to our moles of acid. And that is called our endpoint. So there's a couple different ways, and we'll talk more about some of these ways on the next slide, on the last slide. But what we'll be using in the lab is we'll be using what's called an indicator, where it changes color when we reach our endpoint. And so the indicator, and this is called, sorry, I should put this up here. This is called the equivalence point. When we have equal moles of acid and base, that's referred to as our equivalence point. And so the indicator we'll be using is as soon as we go 1 drop past that equivalence point, this solution then changes color. And it's no longer, in our case, going to be clear. It's going to turn a pink color. And we'll talk about this more on Thursday in the lab. The goal is you're going to do multiple trials, because most people usually go way past the end point in their first trial. The goal is to get just the faintest, slightest pink, because like I said, once we go 1 drop past this equivalence point, we're no longer at a neutral solution. So we'll do multiple trials, so you can try in each trial, hopefully get closer and closer to stopping exactly at the equivalence point. And then the other way we could tell that we're at the equivalence point is with the pH meter. We'll talk more about that on the next slide. And if we used a pH meter, we could create what's called a titration curve, which is what's up there in that picture on the top left-hand corner. So it just plots how the pH of this solution is changing as we add more and more base. So the titration curve plots the volume of the base that we're adding versus the pH, so we can see how the pH has changed as we go from absolutely 0 base in our flask down here to being at the equivalence point and then beyond. So what you're seeing here is we have the volume of base, and then we have our pH. So what this is showing here is when before we've added any base, when we have just acid, so this is acid, only acid, we have a pH somewhere down here below 7, because again, we said the other day that acids have a pH less than 7, so what's it show? It's showing like a 1 here. So this is acid only. We haven't added any base to it. And then as we start to add some base, so we open this up and let some base go in, it'll start increasing the pH. And then right here, this is our equivalence point. When you see it jump up, that's why one little drop past the equivalence point can take you from having an acidic solution to a basic solution. So this represents our equivalence point, where we've had equal moles of base added to our acid. And again, if this is well, you can't really tell from this drawing here, but if we have a strong acid, strong base, that will be at 7. And then if we keep adding more and more base, anything beyond this, after this part, this is only base. So the pH, so we're decreasing the acid here as we add more base. And then at the equivalence point, this is the salt and water only. And then anything after the equivalence point, we have, well, I shouldn't say only base, I'll just say, I should say excess base. So that's why the pH keeps going up and up. So that's what we call a titration curve. But in order to plot the pH, we need a pH meter down in here that will give you what those values are as we add base to the solution. Okay, so here, and again, this is kind of what you'll be doing in your pre-lab as well as in your post-lab questions of trying to figure out what the concentration of our unknown solution is down here. So the question says we're using 15 milliliters of a 0.05 molar sodium hydroxide to titrate 25 milliliters of acetic acid. And it wants us to figure out what is the acid's concentration. Okay, so we're trying to figure out, we don't know the molarity of the acid, but we do know we have, what, 25 milliliters? And then we're adding a total of 15 milliliters of 0.05 molar sodium hydroxide. We're adding that to the flask. So this is where we can use the MAVA equals MBVB to figure this out. But we do have to do a mole ratio, which that is because we've got a chemical reaction going on here. So this mole ratio is coming from our moles of acid and base, because we are doing a chemical reaction. In the last chapter, we didn't have to do that because we weren't doing a chemical reaction. We were just diluting a more concentrated solution to make a less concentrated solution. It was just a physical change. There was no chemical reaction. But because this is a chemical reaction, we have to include, if we have any coefficients here, we have to include that in our mole ratio. Okay, so I'll squeeze this in here. So we have sodium hydroxide plus acetic acid forming. Okay, so our sodium and hydrogen are going to trade places to make our salt, which will be sodium acetate, and then water. Now I will say, I use this because it gets so boring always using hydrochloric acid. Technically, if we were to plot this here, because this is a weak acid, the equivalence point would be higher at a higher pH. You don't need to worry about that. we're just gonna look at this calculation. And everything, so again, this is a chemical reaction, so we have to balance. Everything is balanced. So our mole ratio in this case will be 1:1. So mathematically, this really isn't important for this example, but if this were not all 1:1, we would have to, the mole ratio would affect our values, okay? So we're solving for moles of acid, molarity of acid. So we're gonna do MB times VB over our volume of acid. And again, technically, we have to multiply by the mole ratio. And just like in our regular stoichiometry, this is gonna be our moles of our unknown over our moles of given. So just like we've been doing, which in this case, it's not, mathematically, it's not gonna do anything because we have 1 mole of acetic acid, oops, C2H2O2, there we go, over 1 mole of the sodium hydroxide. But if it weren't 1:1, that would be important. So then we can just plug in the numbers that it's giving us. So our molarity of our base is 0.05 molar. And it took 15 milliliters. Now just like in our dilution equation we used last chapter, with this one we don't have to change it to liters unless you want to. So we can keep it in milliliters over our volume of acid. So we started out with 25 milliliters of acid. And then again, technically, we have 1 mole of acid over 1 mole of base from our balancing. Okay, so then when we plug all that in, that tells us gives us 0.03. So our molarity of our acid is equal to 0.030 molar. And so that's what you'll do in the lab on Thursday. You'll start with a certain volume of the acid. We don't know its concentration. You're going to have a certain concentration of base. And through your indicator, you'll know how much base you're going to add. And then you'll plug it in here to figure out what the concentration. So it's the concentration of this acid is 0.030 molar. Okay, but again, because technically this is a chemical reaction, not just a dilution, a physical change. This is a chemical change. We do have to include the mole ratio. Here it didn't affect our answer, but if it weren't 1:1, it would change what our answer is. Okay. All right, and then finally, so I was talking about indicators. A pH meter, if we wanted to do a titration curve, we can use a pH meter and like record the pH after we add so much from the burette. So the pH meter is just an electronic device that has an electrode. We stick down here into the flask and it measures the pH. It just tells you what the pH is, and then we add base, the pH changes, we add more base, the pH keeps changing and changing and changing, and we could make a nice curve. So that's going to give us a really exact value for if we wanted to solve for the what the concentration is, or just wanted to draw a titration curve, because those are very accurate. We've used pH paper before in one of the labs, the copper lab. You used some pH paper to test what the pH of the copper solution was that you made. So you just dab a little bit of the solution on the little paper strip and then match it up to what color it is on the vial to tell you what the pH is. That gives you a more general, number. And then, as I mentioned earlier, this chart up here on the top right-hand corner, that shows a bunch of different chemical indicators, which is what we'll be using in the lab. And they will change color at different pHs. So you can see there's a whole bunch of them that change colors. Some change colors way down at a pH of 1 or 2. Some don't change colors all the way up till a pH of 10 or 11. The one we're going to be using is called phenolphthalein. That's a fun one to spell. That's a good spelling bee. It is clear while you have an acidic solution. So the whole time you have an acid, it's a clear color. And then once you go over to the basic side, it turns a real bright pink. Not my shirt on it. Miss Gilmore has more of a pink shirt on. It will turn a really bright pink, and the more base you add, the pinker it will get. Okay, so that's the indicator that we're going to use because we're titrating an acid with a base. So we want to see when it flips over to the basic side. So that's why we'll use phenolphthalein. But if we were using other acids or bases that are going to have a different equivalence point than 7, we could use any of those other ones. And there's even natural indicators all around us, like hydrangeas. They're starting to come out right now. The color of the hydrangea flowers tells you the pH of your soil. They're what we call natural indicators. So hydrangeas are probably the most common. There's a bunch of, I'm terrible at growing hydrangeas, but they're all over. Even this here is a chart of different food, like beets, blueberries, grape juice, all sorts of different plants or foods that change color based on their pH. So they're what we call natural indicators. And then finally, buffers. We're not going to do any calculations with buffers, but it's just a vocabulary word. We do calculations with buffers in AP. These are solutions that resist changes in pH, which your body's full of buffers because your body wants to stay in like your bloodstream pretty neutral. But again, there's a lot of foods and stuff that we eat that could change the pH of our body if we didn't have these buffers. So they're just solutions that resist changes to pH.
Could like someone giving off like hydrogen gas, could that be a chemical indicator?
No, because hydrogen gas is not hydrogen ion. Hydrogen gas is H2. So yeah, again, pH is hydrogen ion. Okay. All right, so that's it for our notes. And again, besides the homework that I'll give you now, you also have the pre-lab due for next class. So you can also be working on